make sure this thing is working. So, as a continuation of these concepts that we were talking about last time regarding osmosis, depending on what cells are exposed to, fluid can flow from one compartment to another. So it turns out that this concept of osmosis is critically important physiologically. Everything that's written in this slide, which is very wordy, we just have that in here for your information. I'm going to refer to this picture, which is obviously better than just having words on the slide. It turns out that as blood is flowing through our circulatory system, there's two types of pressures that you need to consider. First is what we call the hydrostatic pressure, which is the pressure of the fluid being pushed by the heart pumping and its pumping activity through the blood vessels, just as if they were pipes, like water flowing through pipes. There's a certain water pressure that you have in your pipe, and if you don't have enough water pressure, then the water doesn't come out of the tap, right? So that's what we call the hydrostatic pressure. And then we also have the osmotic pressure. So osmotic pressure is simply the presence of solutes between different compartments. When there's differences between them, then the water is going to flow in the appropriate direction. Remember, from where there's more water to where there's less water, so from a more dilute to a more concentrated solution, or dispersion to be more exact. Again, it includes colloidal dispersions and suspensions. In order to attempt to dilute those components that are separated by the semipermeable membrane. So it turns out that our blood pressure, our hydrostatic pressure, at the arteriolar side starts at about 35 millimeters of mercury. It turns out that the osmotic pressure of the components of the blood that are then attracting water in that direction, because there's a lot more particles and things contained within the circulatory system than there is just kind of floating around in the interstitial fluid. So there's a opposing osmotic pressure that's coming inward. So our hydrostatic pressure, as the blood flows through your smaller blood vessels and proceeds from arterial to capillary to ultimately coming out from the venous side, that hydrostatic pressure changes or drops from about 35 millimeters of mercury to about 25 millimeters of mercury. So there's a change in that, to about 18 millimeters of mercury. This is the one that's the hydrostatic pressure, the one that's going out. So there's about a half, it's reduced by about half. If you compare that to the osmotic pressure, it turns out that the osmotic pressure, unless you're losing contents of what's inside the blood, that doesn't change much. So if you do the difference, it turns out that at the arteriolar side, there's a net filtration pressure of about 10 millimeters of mercury. And what that ultimately results in is a certain amount of water, fluid, moving from the circulation into the interstitial fluid. If you go to the other side, the reduction of the hydrostatic pressure to 18 with a minimal change in the osmotic pressure then produces actually a negative filtration pressure. So what that means is that water will flow back into the circulation. But if you look at those numbers, there's a net filtration positive of about 3 millimeters of mercury going outward. So what that means is that you are constantly losing fluid from your circulation. That fluid is going into the interstitial space. And this is what the lymphatics are responsible for. So all of that fluid ultimately gets absorbed by the lymphatics. You may not be aware of this, and because we're not, it's just part of physiology, but about 24 liters of fluid a day gets filtered out of your circulation. About 20 plus comes back, so you don't really notice much. And then, of course, the deficit, the difference, is what the lymphatics ultimately recover, and all of that comes back into the circulation in the chest and the thoracic duct. But the osmotic pressure of the circulation is critically important in determining the balance between how much water is filtered out and how much water is coming back. If this osmotic pressure, which is reasonably constant in your blood, is for whatever reason altered, changed, and the most common cause is disease of some kind, then that can lead to major changes in the fluid homeostasis, this whole process, and that can lead to major problems. So this is what everything that I've said is in this slide in words. I thought it was better to describe it in using a picture. So again, whenever there are changes in the concentrations of particles that are dispersed in any bodily compartment within which there can be fluid shifts or fluid exchanges, that can be either the source or it can actually be the manifestation, the consequence of disease. So for example, one of the major contributors to the osmotic pressure of your blood is the proteins, the plasma proteins that are in your blood. The liver turns out to be the primary producer of plasma proteins. Even though proteins make up less than 10% of plasma by total mass, it turns out that even a small deficit in the production of plasma proteins by liver, if you have liver disease, that can lead to a significant reduction in the osmotic pressure of your fluids if this number goes down significantly. So again, disease can lead to changes in concentrations of particular components of bodily fluids that have an influence on the shift of water between compartments. One of the primary participants in these issues is the liver. The liver is the primary producer of plasma proteins. Whenever you have a liver disease, you have or can have deficiencies in protein production. The moment you have deficiencies in protein production, the osmotic pressure of the blood changes to the point that it can be significant in this process of fluid shifts between blood and tissues that surround it. The kidney, of course, is the other one. The kidney is responsible for the maintenance of the concentrations of a wide variety of different solutes that exist in your bodily fluids, particularly sodium. You can also have issues with kidney disease in which protein is being lost in the urine. When you have, normally proteins are too big to be filtered by the renal glomeruli, but when there's kidney disease, they can become leaky. Not only can they leak solutes, they can also leak proteins, and that can lead to imbalances between filtration, reabsorption, and all kinds of issues related to homeostasis of solutes and particles that are dispersed within your blood, and ultimately all of that can lead to severe changes in the redistribution of fluids, and that can of course then lead to exacerbation of the disease. So when you see patients, those of you who are going to be seeing patients in all sorts of places, intensive care unit, even the floor, in the emergency room, you will see patients that have all kinds of fluid imbalances. And in many cases, it has to do with imbalances in solute, proteins, and all kinds of issues that are going on in their bodily fluids, which causes problems with their fluid distribution. All right, just very briefly, we only had a handful of slides to finish. So just to recap some concepts related to density, just briefly talking about viscosity. So as we know, density is the ratio of mass to volume of any substance. It can be pure, it can be a mixture. And if we're talking about a dispersion, when you add more solute or more dispersed phase into a dispersion medium, the more particles are in there. Typically, again with very few exceptions, there's going to be an increase in the density. Typically what happens is that the increase in mass is not met equally by the increase in volume, so the mass increases in greater proportion than does the volume when you're mixing things, particularly when you're dealing with solid solutes. And that then causes the numerator to increase in excess of the denominator, so mass to volume ratio gets larger, density goes up. This is the classic situation. Right, so here you have just more than a handful, a good number of examples of substances. These are all ionic compounds, but this is also true for biochemicals, typically proteins and large colloidal-sized particles. The more of them you have in water, the greater the density of that particular dispersion. So again, this is just to sort of illustrate these processes. And this is what I said. The increase in mass is larger than the increase in volume. So with density, in most cases, particularly in biological fluids, which is where we need to have the discussion, because if we're talking about all kinds of random things that people study in the lab just for the sake of studying them, you can probably find liquids that, as you increase the components of the mixtures, they may not necessarily display an increase in viscosity. But when you're looking at biological fluids, which is what we're concerned with, this is pretty much one that you can take to the bank. Viscosity is simply, it's a measure of the resistance of a fluid to flow. It pretty much means how thick the liquid is, right? So the classic example of viscosity, if you were to use one word, typically we use food to describe these things. Molasses is a good one. I usually use ketchup, mayonnaise. All of those things are very viscous. If you try to pour ketchup, it's going to be like, right? And then molasses is a good one, yeah, because it's going to take its time, right? So it's very viscous. It's very thick, right? So it turns out that density and viscosity tend to go together. So when a liquid is more dense, it also tends to be more viscous. Particularly when you're dealing with mixtures, dispersions, right? It means there's more things in there. That goes with density, that also tends to go with viscosity. So where this becomes relevant is in particular with blood, because the viscosity of blood is established by not only its dissolved or dispersed components, but also its suspended components, particularly the cellular components. So the viscosity of blood is critical because if blood is too viscous, then it has problems reaching and being distributed through the body, right? It can limit the ability of the heart to properly pump, because if you're pumping a very, very thick fluid, imagine pumping molasses down tubes. I mean, it's not going to really work very well, right? So the more viscous the blood is, the greater difficulty for pumping, the greater difficulty for perfusing. That means there's greater difficulty in delivery of oxygen. Also, remember, blood serves to remove waste products from tissues. So that entire process of delivery of essential nutrients and removal of waste products, all of that becomes compromised. So one of the things that can be measured when you send out a blood sample is density. Okay? And then if you measure the density, that correlates with the viscosity. And then you have to go fishing. Why is this blood so dense? Meaning it's very viscous. So then that can lead to all sorts of problems. So many cases, patients will come in with signs and symptoms. They're short of breath after going up 3 steps. They have all kinds of problems with tingling in their extremities because their blood isn't reaching all these places properly. They're having chest pains and things of the sort. So in some cases, you can rule out heart attacks and other things. And then it turns out that it can be increased viscosity of the blood, right? So there are particular diseases that can result in this particular problem. And typically, one of the most common scenarios is a disease called polycythemia vera. So this is it's a blood disorder. Amongst all blood disorders that you may have learned about, leukemias are part of them. For example, too many white blood cells. You can have too much platelets, thrombocytosis, and then you can have polycythemia vera, which is too many red blood cells. And because these are the most numerous cells in your body, if you have a malfunctioning bone marrow that's producing too many red blood cells, then your blood is very viscous. And as we've said, this not only comes with the problems of delivery of oxygen and removal of waste products, but again, it's the pumping. The heart has to work much harder to pump this very viscous blood, ultimately can lead to heart failure. So this is a disease that typically appears earlier in age. And if you have a 35, 40-year-old person, or even younger, but middle-aged person coming in with heart failure, that is not a common situation. I mean, typically heart failure is with people who've had long-standing hypertension or diabetes or all kinds of other things that they're in their 60s and 70s. You have a young person coming in with heart failure, then this is one of the more common situations, and it's due to viscosity of blood. You can also have problems with the liver. Back to the liver. If the liver is, for whatever reason, here would be the opposite scenario. Instead of not producing enough protein, it's producing too much protein. Or you have a disease like multiple myeloma, for example, where your white blood cells are producing massive amounts of immunoglobulins, i.e. antibodies, just because, for no reason whatsoever. It's a disease, it's a blood disorder as well. Too much protein in your blood can also lead to an increase in the viscosity of the blood, and then it comes with all of these problems. So all of these, any situation that increases the content of substances dispersed can ultimately lead to disease because of that increase in dispersed substances. All right, everybody's with me? Oh, the recording's back, so it did start. There's going to be a gap, but anyway. Okay. So that is chapter 6. We're going to now move on to chapter 7, which is the chapter on acids and bases. So this is a foundational chapter. As we're going to see as we move forward, these concepts are going to carry on for pretty much the remainder of the course, many of them anyway, because when we start talking about biochemistry, pretty much not all of them, but the majority of biochemicals that we're going to talk about, they display in one form or another acid-base properties. And acids and bases are critically important in determining all kinds of outcomes in not only laboratory chemistry, but the behavior of these types of compounds are critically important in metabolism and all kinds of things that we're going to be learning as we move forward. So, this class of compounds, again, acids and bases, as we're going to learn, they sort of have opposite behaviors. These are fundamental compounds. Classes of compounds for both human biochemistry and physiology. As I've said, nearly every biologically relevant compound that serves any type of critical role in sustaining life displays some kind of acid-base property. The structural and functional integrity of nearly every biological compound depends on the acid-base content of the medium in which they existed. Okay? So if there's alterations in how much acid or base is present in those bodily fluids that bathe everything that exists within the human body pretty much, that can lead to enormous dysfunctions and malfunctions, and then everything goes south after that. Okay? So one of the primary roles of physiology, not only is it what we discussed in the previous chapter, which is to maintain a perfect or near perfect balance of water versus dispersed particles, to maintain a near normal or constant osmolarity throughout bodily fluids. The second or amongst the very top roles of human physiology is to maintain the adequate acid-base ratio in all of your bodily fluids. Because the moment that goes in the wrong direction, that's the end. Everything goes south after that. Okay? So, of course, because people get ill for a wide variety of different reasons, acid-base disturbances are, in fact, at the very core of many, many pathophysiological processes that are either the source or they become manifest as disease. So many, many disease states, there is some connection with acid-base disturbances. So we need to have an understanding of structure, function, properties of acids and bases so that you can call yourself a well-educated and well-trained health professional. So again, the learning objectives are here, FYI. We'll let you look at them. We're going to start by simply defining what acids and bases are. It turns out there's 3 levels of definition. There's one that's the biggest umbrella, and then you can narrow it down to a certain class of compounds, and then when you're dealing with aqueous systems, which is what's most important in biological systems, then we're going to narrow it down to that as well. So we're going to start with some simple definitions, simple concepts. So acids and bases are everywhere in your daily lives. You may not realize it, but it turns out that they are. So historically speaking, acids and bases have been characterized based on the display of particular chemical and physical properties. So, because historically, and this is true for medicine as well, I think we've had this conversation in the past, historically speaking, everything has gone into the mouth. Okay? Everybody tastes everything, tasted everything, right? Including urine and all kinds of things, right? Anyway, so acids historically have been defined by having a sour taste, and most acids, particularly if they have enough concentration, will actually dissolve metals. It's not that they actually dissolve the metals, it's that they actually react with the metals and they destroy them, and then what's left dissolves, right? But the metal's gone at that point. So some acids on the left, right? Lemon juice has what kind of acid? Citric acid, right? We're going to talk about citric acid later because it's the critical component of the citric acid cycle, which is Krebs cycle. You may have heard of at some point in your life, right? Vitamin C is also called
citric acid.
No, not citric acid. Anybody know? A layperson will call it vitamin C. A scientist would call it ascorbic acid. Ascorbic acid. It's an acid. This one in the back, this is vinegar. What's vinegar? Acetic acid, right? And then in baking soda or baking powder or whatever this one is, there's a mixture of different acids. The one on the right, which is also shown here as a base, it actually also has acid behavior. We're going to talk about that. But acids are everywhere, right? Bases have been associated with a bitter flavor or taste, right? And if you put your hand touch it directly in a solution of a base, of course, don't do this in a concentrated base because if you put your finger in it, it's not going to come back out. You're going to lose it. But dilute, you can actually put your hand, even sodium hydroxide, you can 0.1 molar, 0.01 molar, very dilute, it's fine, nothing's going to happen. Just touch it, it feels like it's soapy, like slippery type of thing. Unlike acids. Acids are not that way, interestingly. So, so what are the flavors that we have in the human body? What are the tastes? How many tastes can we taste? Sour, bitter, sweet, salty, and that's it. There's a fifth one, which is umami. Umami, right? Yes, there's a fifth one. If you're not aware of umami, what is you can actually put something on food that will trigger umami. You can actually taste it just like you can be blinded by a thing, and you can put your finger in a little bit of sugar and taste it. Oh, this is sweet. Oh, this is bitter. Oh, this is sour. Salt, it's salty. And then there's another one, you go like, ooh, it's umami. Anybody know?
Tomatoes?
No. Well, many foods have this, or something that triggers umami, but there's a specific seasoning that you can use that is triggering umami.
What that's in Chinese restaurants.
Yes, and many have banned it because of some nonsense of history, but anyway, I'll talk about that in a moment. Yes? MSG, monosodium glutamate. It's the best thing on the planet. You may have heard historically, oh, MSG, it's the bad thing, it's the devil, don't eat MSG. No. There's been historical associations with people that have, and there's an association with Asian food because it turns out that soy sauce also has large amounts of things that trigger umami. Fish sauce, oyster sauce, different things. They have things in it. MSG is just monosodium, so you're taking sodium as in sodium chloride. And then the component is glutamate, which is an amino acid, one of the major components of all proteins. There's nothing wrong with MSG. Okay? It's the best thing on the planet because believe me, trust me. I buy it in this. I go to the market basket here in Lowell where this is this big MSG, right? And it's next to my salt shaker, right? When you're seasoning steaks, fish, chicken, whatever, right? Season it however you want, and then as an added bonus, because it's going to be a bonus, add a little MSG and then sprinkle it and then cook it. You're going to thank me for it. Believe me, it enhances the flavor of everything that you're going to eat. Obviously not something sweet because it's kind of savory. It's savory, but it's not salty. You're going to realize it's not salty. It's a different thing, right? And it's like, oh my God, after you discover that, oh my God, how have I had this all my life without having this? Anyway. So here's acid and base, it turns out, right? So on the left, sodium hydroxide. Here's hydrochloric acid. If you take a can of Coke, which is pretty much aluminum, right? I mean, look at this. Sodium hydroxide, right? And here's HCl, right? I mean, it's gone, right? So this is why they say it dissolves. Well, not really. It's destroying the damn thing. It's completely, it ultimately gets dissolved because it gets destroyed, right? All right. So as you're going to learn in the lab, one of the applications of these types of compounds, if you go in nature and you extract all sorts of materials from organic sources, many, as I've said, many organic compounds that exist in nature, human body included, but many plants and other sources, they produce all kinds of different compounds. The plant world is just an amazing collection of the most complex structures. Only plants have that power. They make these enormously large complex structures that have acid-base properties. And then depending on how much acid or base they're exposed to, these compounds, they exhibit color. Okay? So depending on how much acid or base, you can then create a series of compounds, which in the lab you're going to learn we use them as what we call indicators, that depending on how much acid is in there is the color they exhibit. So you can use these natural compounds to serve as a visual test to tell you how much acid or base is in your sample. Okay, so you're going to learn about all this in lab. So the whole gamut of colors, from colorless to yellow to green to blue to purple to whatever, right? All colors can be displayed depending on what substance you use and depending on how much acid is what color they're going to exhibit. So you can actually measure very qualitatively, in some cases semi-quantitatively, how much acid is in your sample by simply having a list of all of the possible indicators that are out there and at what content of acid they produce a color. So depending on what you see in your sample, you can then list, oh, this is this much acid because it's green. It's that much acid because it's purple, right? You can do a whole analysis, and you're going to learn about this in the lab. Now let's talk about, at the molecular level, what's happening chemically. So it turns out, we're going to start with the broadest definition, the most inclusive, which is what is known as the Lewis definition of acids and bases. So a Lewis base, I'm going to start with the second one. A Lewis base is any substance who at the molecular level contains a pair of electrons that it can provide to another atom and thereby form a coordinate covalent bond. So we define coordinate covalent bonds in the first half of the course. Very simple refresher here. Whenever a bond is formed between two atoms and one of the atoms provides both electrons in the bond, that is known as a coordinate covalent bond. Okay? So the substance that provides the electrons is known as the Lewis base. The atom that accepts the electrons and thereby forms a bond with the base is known as a Lewis acid. Now, if that atom, Lewis acid, is capable of accepting a pair of electrons to form a bond, that means that it must have some kind of an electron deficiency or some kind of a vacancy in order to accept that pair of electrons. So it's typically an atom that has some kind of a vacant orbital, or it can be an atom that is having a full octet. That's not shown in this slide, but I'm saying it. It can also be an atom that is bonded to something that's very electronegative, that's attracting electrons in that direction. It's leaving that atom somewhat electron deficient, so therefore something can come from the opposite side and form a new bond, and then that establishes the Lewis acid-Lewis base interaction. So Lewis acids and Lewis bases are amongst the most important types of compounds in biochemistry. For example, we've already talked about previously about hemoglobin and how iron is latched onto the heme structure and how that heme structure latches onto the globin protein. We learned about this in the context of coordinate covalent bonds, it turns out. And we learned about the oxygenation process, right? That oxygen ultimately binds to another position on the iron. So it turns out that the iron is bonded to these 4 nitrogens. 2 of those bonds are bona fide normal covalent bonds, and by that I mean each atom provides 1 electron to the bond, they come together and they share. In the case of the other 2, here they're shown as all being the same, but this is what it turns out to be. The other 2 are actually coordinate covalent bonds. The nitrogens are providing a lone pair. The iron accepts those lone pairs to form the bonds. So there's another coordinate covalent bond that's formed by an appendage that's coming from the globin protein, which is an amino acid component, and I'm going to draw the lone pair here to exaggerate. That lone pair is donating, that nitrogen is donating a lone pair, 2 electrons coming from the nitrogen. The iron latches on to that lone pair. That's what secures the heme onto the hemoglobin. Okay? It's that little arm that's coming out of the protein, which is that histidine residue over here. This is what we're going to learn about this when we talk about proteins. And the protein produces this little piece over here, which is actually a piece of an amino acid, which is one of the building blocks of proteins. That latches onto that iron. And then the oxygen, when it's time for the oxygen to come along, when this hemoglobin is getting close to the lungs, the oxygen has 2 lone pairs, right? It's technically a double bond, right? Each oxygen has 2 lone pairs. One of those lone pairs is forming a bond to the iron. That is another coordinate covalent bond. So, iron is a Lewis acid in all of this process. Iron is a Lewis acid. It's accepting electrons from the nitrogens. It's accepting electrons from the iron. Here's another important compound without which we would not be able to have this conversation. Anybody know what the functions of vitamin B12 is? If you have vitamin B12 deficiency, what do you develop? You develop anemia, right? And there's different ways that you can develop anemia if you have vitamin B12 deficiency. We talk about this, in fact, in the first half of the course in one of our IPE activities. So you can do a test to determine where the source is. So in this case, this is the only biological compound known, and actually this is a variant of the compound. There's 2 versions of vitamin B12. This is not the one. I was going to say something else, but anyway. This is a compound here. Notice, again, similar to the iron in heme, the cobalt in this case is held in place by 1 covalent bond. That's the solid one. There's another covalent bond to the hydroxy group. And then these ones that are in dotted lines, these are coordinate covalent bonds to nitrogen. So cobalt is a Lewis acid, right? These nitrogens and the oxygen and this other nitrogen, there's a lone pair on that nitrogen. They're not showing the lone pairs, but there's a lone pair on this nitrogen here, right? That's what's actually forming this bond. There's another one here that's forming that bond. There's another one there. These are coming from the nitrogen. Same over here, right? cobalt is acting as a Lewis acid in that particular reaction. And this is two of many, many, many examples of biological structures that are held together, whose structural integrity and ultimately their functional integrity depends on these Lewis acid, Lewis base interactions. The second definition that is just as relevant even in biological systems is what we call the Bronsted-Lowry definition of acids and bases. And in this case, the focus point is a proton, a hydrogen ion, positively charged. So a Lewis acid will contain, a Bronsted-Lowry acid down here will contain a positively polarized hydrogen atom, or it will simply be able to provide a H plus hydrogen ion, which we technically call a proton because it's a proton. So the formal definition is any substance, technically it's a Lewis acid, but what's specifically being provided is a proton. The species that picks up that proton by way of a lone pair, so technically it's acting as a Lewis base, but if that Lewis base is specifically binding to a proton, that's when we now call it Bronsted-Lowry. So if it's a lone pair binding to anything other than a proton, that's when we call it a Lewis acid-base transformation. If the Lewis acid is specifically a proton, a hydrogen ion, or hydrogen atom that's being picked up from something else, that's when we narrow it down to only protons. That's when we call it a Bronsted-Lowry acid-base process. So the acid is the one that provides the proton. The base is the one that picks up the proton. So here, these little cartoons that we found on the internet, you can find anything on the internet. I'm sure everybody's aware of that, right? These little cutesy cartoons over here with the little acid with this little cute little hat and his smiley face, donating his protons, right? And then, of course, the base is here with the open arms. Here, give me those protons. I'm going to pick them up. So this is the base that's picking up those protons that are coming from the acid. Now, you can go further and restrict the definition to only happening in aqueous systems. In this case, we call it an Arrhenius acid or Arrhenius base. Any substance that upon dissolving in water produces, or in fact, as we're going to learn, increases, because there's already some in there, very small amount, increases the amount of hydronium, H3O+. If the substance upon reacting or dissolving in water increases the concentration of hydronium, that's an Arrhenius acid. Conversely, if the substance upon dissolving releases hydroxide, that is known as an Arrhenius base. So if you were to draw the Lewis structure of hydronium, it looks like this. There's a plus charge on the oxygen. And if you realize, what is in fact hydronium? Hydronium is a water molecule that has picked up a proton. Okay? So technically, water is acting as a Lewis base, and it's picking up a Lewis acid, which is it happens to be a proton. You can also look at it from the perspective of a Bronsted-Lowry definition. Water is the Bronsted-Lowry base that is picking up a proton from whatever Bronsted-Lowry acid is providing that proton, and in doing so becomes hydronium. But because that is what happens with any acid that dissolves in water, they always will end up producing hydronium, then we simply restrict the definition by defining any substance that upon dissolving in water produces hydronium, that is an Arrhenius acid. So this is the most relevant definition in aqueous systems, including biological systems, because in biochemistry everything happens, or nearly everything happens, in water. So any acids that enter aqueous media are going to ultimately produce hydronium because there's water in there. Hydroxide is the counterpart. When the substance upon dissolving in water produces hydroxide, then that is known as a base. So when we talk about, you probably have heard of this, we're going to explore that in much more detail now, but when an acid reacts with a base in an aqueous solution, what's truly happening is that hydronium is reacting with hydroxide. They neutralize each other, and that's in fact a word, a term, a scientific term. Neutralization is when an acid and a base react with each other. In the case of an Arrhenius system, what happens is that the hydronium will ultimately donate its extra proton to the hydroxide, right? So the hydroxide comes along, picks up this proton from the water. Well, if you have hydronium losing a hydrogen atom in the form of H+, it becomes H2O. If you have hydroxide picking up a proton, it becomes H2O. So therefore, what you end up with is two water molecules. Okay? And that's what we call a neutralization reaction in an aqueous system. So this sort of summarizes these concepts. A Lewis definition is the most inclusive, the broadest. You have some lone pair coming from some atom, whatever that may be, and that's being accepted by some other atom, whatever that may be. Doesn't have to be a proton, doesn't have to be anything other than an atom that can do that. That's the Lewis definition. If your base is any base, like the one in the Lewis definition, but your acid is specifically a proton, then we're talking about the Bronsted-Lowry definition. So there's a little bit more restriction in terms of what the acid is. And then if you're talking about the Arrhenius definition, we're specifically talking about hydroxide and hydronium being the reactants in the process. So remember, hydronium H3O+ can be represented by H+ aqueous. Okay? H+ aqueous means that you have a proton that's surrounded by water. Well, what's truly happening is that the hydronium, the proton is actually technically latched onto the water, right? So here's the proton, and here's the water, right? So H+ aqueous is synonymous with hydronium. So it's not uncommon to represent an acid, particularly in an aqueous system, as simply H+, because that's the source of H+, that's then ultimately ending up in the solution. So acids and bases, as we've discussed, are everywhere. There's many applications, and this is a very short list. So this is just some common acids and bases. So many of these you probably haven't really had any exposure to, but hydrochloric acid is one very important one. This is in all sorts of places, but in terms of physiology, where is HCl important? Stomach acid, well, you actually literally stomach acid. Your stomach is producing, as you sit here listening to this discussion, hydrochloric acid is being produced by your stomach cells. And when you're hungry and you don't have anything in your belly and it starts growling and whatever, acid starts to accumulate, and ultimately that's sort of to tell you that you need to eat something. And of course, if you see food but you're not able to get to it, then it gets worse, and then it's a whole thing, right? Anyway, so sulfuric acid also used in all kinds of places, fertilizers and things of the sort. Nitric acid, this is a very important industrial compound. It provides nitrogen that then can be used to produce all kinds of fertilizers, explosive dyes, and all kinds of different things. Sodium hydroxide, very important compound used in all sorts of places. The main component of Drano is sodium hydroxide, extremely concentrated. So that's the one you want to put your finger in there because it may go down the drain with everything else. Right? So just be careful with that. And then, so any source of hydroxide is technically a base. Now, ammonia is a base as well, as we're going to see. We've already seen this, but you may not have been aware at that point. Ammonia can be looked at as a Bronsted-Lowry or a Lewis acid base if there's no protons. This actually, as we're going to learn, when it dissolves in water, it actually produces some percentage of hydroxide. That's why you can call it a base, according to all three definitions. So again, let's dissect this in terms of the three definitions. So when HCl dissolves in water, technically is producing hydronium and chloride. So again, the water is picking up the atom, a atom that has an electron deficiency associated with it. So if you remember, this has a delta plus on hydrogen, a delta minus on chlorine, and then oxygen has two lone pairs. Those lone pairs are attracted to that electron deficiency. That technically then, the HCl is acting as a Lewis acid, and then a new bond is formed between the oxygen lone pair and that other atom. It happens to be a proton, right? So because it happens to be a proton, you can also look at it from the perspective of the Bronsted-Lowry definition, that the HCl donates a proton to the water. The HCl is the Bronsted-Lowry acid. The water is acting as the Bronsted-Lowry base because it's picking up that proton. And then, of course, the outcome is the production of hydronium. So you can also describe it in terms of the Arrhenius definition, in which by dissolving this substance in water, you produce hydronium, then it automatically makes it an acid, right? This is trying to illustrate it with little cartoons over here. These are the hydronium particles. This is the chlorides that when the substance enters water, it completely splits apart pretty much and produces that compound. And then from the perspective of hydroxide, for example, when hydroxide enters water, it can actually exchange protons with the water. So that establishment of a bond between the oxygen of the hydroxide and an atom from the water, whatever that atom may be, is what classifies it as a Lewis base. Because that atom is a proton, you can speak of it as Bronsted-Lowry. Just by merely dissolving that hydroxide in water, it releases that hydroxide into the solution. That then defines it as a Arrhenius base. Okay, so you need to be able to look at a reaction or a transformation or a process and establish whether it's acting as one or the other, right? In this case, because it's aqueous, all three are applicable. But if there's no water, the Arrhenius definition is non-existent. If there's no protons involved, then the only thing you can speak of is Lewis acid and Lewis bases. Okay? All right. So one of the critical pieces that we need to understand in this discussion and moving forward is the fact that for most acids and bases, and we're going to focus on aqueous systems, so it's pretty much related to the Bronsted-Lowry and Arrhenius definitions. When an acid dissolves in water, it turns out that for the vast majority of acids, the reaction does not go to completion, meaning that the transfer of that proton from the acid to the water is not 100% complete. So the process is then reversible, meaning that there's an equilibrium that is established between the acid in its intact, unionized form, meaning it has not split into its corresponding ions, H+, and in this case, Cn-. So this is the unionized, and then over here would be the ionized form, right? Notice that the proton of the HCN is now been incorporated as one of the protons in the hydronium. So an equilibrium is established in which you're going to ultimately have a certain proportion of HCN left unreacted. This is just an example. It can be H. You can call it HX. It can be any acid, right? This would be X- if that were the case. So hydronium results from water picking up the proton to produce the hydronium, and then the cyanide in this case. Literally cyanide. The cyanide that's a poison. That's what it is. So it's Cn-. So if you start on the left, you can clearly identify that the acid is HCN because it donated its proton to the water, right? The water picked it up, and that's how it became hydronium. And then what's left from the HCN is the Cn-. But if you start on the right and you imagine the reaction going backward, in that case, the hydronium is the acid because it's giving up its proton to the cyanide. That regenerates the water and regenerates the HCN. So what turns out to be the case is that in every acid-base reaction, you can always identify an acid on the left and a base on the left, i.e. the reactants. And you can always identify another acid on the right and another base on the right, i.e. the products. It's all based on how they react with each other. Again, in an aqueous system, a proton is somehow being donated to something, something's picking it up, right? And that picking it up is water, pretty much, if it's the starting point. But on the right side, the cyanide is the base that's picking up a proton from water. So notice that as you're going from left to right, you're talking about the Arrhenius definition because hydronium is being produced. If you're going from right back to the left, you're talking about the Bronsted-Lowry definition because hydronium is not being produced in that process. All that's happening is that a proton is being transferred from hydronium back to the cyanide. So this is why you need to be very clear about the definitions. But the point is there's an acid and a base on either side. So this is the key point. When you're making that analysis, what you will also always observe is that the acid on the left is structurally related to the base on the right, and they differ by exactly one proton. Everybody sees that? The HCN and the cyanide differ by exactly one proton. If you look at the base on the left and the acid on the right, you're going to observe the same situation. They differ by exactly one proton. Okay? So, we call these structures that are related structurally and they differ by exactly one proton, we call them a conjugate acid-base pair. And every reaction will always have two conjugate acid-base pairs. The members of the pair will always be on opposite sides because they resulted one from the other through this proton transfer process. The acid in the pair will always have one more proton than the base in the pair. Conversely, the base in the pair will always have one less proton than the acid in the pair, right? And we call them conjugate acid-base pairs. So when we're speaking of these entities, you can say cyanide is the conjugate base of HCN. Water is the conjugate base of hydronium. You can also say that hydronium is the conjugate acid of water. You can also say that HCN is the conjugate acid of cyanide. They are related in that conjugate acid-base pair, and they differ by exactly one proton. The acid has one more proton, the base has one less proton. Okay? All right, so here's some examples. Here's acetic acid. Its conjugate base will have one less proton, so it is acetate, which is the base on the right. Here's water. These are all Arrhenius processes, right? Moving to the right anyway. Here's water. Picks up the proton from the acetic acid, and it produces hydronium, right? So acetic acid is the acid in this pair. Hydronium is the acid in the other pair. Water is the conjugate base of hydronium. Acetic acid is the conjugate base of acetate is the conjugate base of acetic acid. Here's another example. This is what happens with ammonia. This is why ammonia can technically be considered an Arrhenius base. Because when it dissolves in water, it actually chemically reacts with the water, picks up a proton from the water, and releases small fraction. It's a very small fraction, but it turns out it produces hydroxide and ammonium with it, right? Because notice, the ammonia picks up a hydrogen ion from water. That's what makes it become ammonium. And then the water donated that proton to the ammonia, and that's how the hydroxide was produced. So notice, ammonia and ammonium differ by one proton. Ammonium has one more proton. So that's the conjugate acid of ammonia. The water, which acted as the acid in this reaction, lost a proton. it became hydroxide. So hydroxide is the conjugate base of water. Water is the conjugate acid of hydroxide. Okay? And this is the one that we've already talked about, right? So what do you notice about water? This is a critical observation, and this is going to take us forward for the remainder of the course as well. Yes?
It can be an acid or a base.
It can be an acid or a base depending on what its reacting partner is. This is a critical property of water. The fact that it can generate, it can react as either acid or base and generate either hydronium or hydroxide, depending on what it's reacting with. This is essential for life. Without this property, we will not be having this conversation. We'll talk more about that in a few moments. So, if you're going to draw not drawing, in this case we're simply identifying which one is acting as the acid, which one's acting as the base. Notice that in these reactions, the first one anyway, there's no water. So this is a Bronsted-Lowry process, right? So which one is the acid on the left for reaction A? So if you observe, this is related to this, and the one on the right has one less proton, right? So that means that this is an acid and this is a base, and they represent a conjugate acid-base pair, right? And then if you also observe this one and that one are related, they differ by one proton. The one on the right has the one more proton, so this is the acid and this is the base. Yes? So hydrogen sulfate, which is HSO4 minus, is the conjugate base of H2SO4, which is sulfuric acid. The one on the left, the second one on the left, hydrogen phosphate, is the conjugate acid of phosphate, which is the one on the far right. They differ by one proton. Okay? If you look at the second pair, which one is the acid?
The one on the left.
Again, it's this one, right? That didn't change in this particular example. So if you notice, this one has one more proton. This is the acid. This is the base, right? And then, in this case, the water resulted from the hydroxide picking up a proton. Hydroxide will always be a base. It cannot be anything else. Okay? And then, of course, water would be one acting as an acid if the reaction were to move backward. So if you analyze the backward process, you'll easily identify. On the top one, the H2SO4 is losing a proton to phosphate, becoming HSO4 minus. If it gave away a proton, it's an acid, right? The phosphate gained a proton to become hydrogen phosphate. So that's what makes that one the base. Everybody still with me? Yes? Okay. So, this is what I'm talking about. When a substance is capable of acting in both capacities, acid or base, depending on its partner, then we call that an amphoteric or amphiprotic substance. These are sort of synonymous terms. And many, many examples of these substances exist, particularly in biological systems. Of course, we've already talked about water. Turns out bicarbonate, this is dihydrogen phosphate. Hydrogen phosphate can also do the same thing, the one that we just saw. Many, many, many biochemicals, for example, amino acids, amongst others, are amphoteric. So this would be a substance that, again, depending on what it's reacting with, it can either accept a proton on the left, here it's accepting it, but it can also donate a proton, depending on what it's reacting. So these properties are critically important for life and for biochemical transformations, as we're going to see throughout the course. So here, for example, is hydrogen carbonate, also known as bicarbonate. If you're going to show the products of the reaction, by which it's either acting as an acid or a base. I said that hydroxide is always a base, right? So in this first one, it's acting as an acid. So what's happening here is the hydroxide is picking up that proton from the bicarbonate. In doing so, of course, it becomes water, and then what you end up with is carbonate, right? This here is a conjugate acid-base pair, and then, of course, the carbonate-bicarbonate is another pair. The bicarbonate is the acid, the carbonate is the base in that pair, and then, of course, hydroxide is the base in the first instance, and water will be the acid in this, if that reaction were to go backward. In the case of the reaction with nitric acid will be an acid because it's a strong acid, as we're going to learn. So that bicarbonate picks up that proton. That produces nitrate. And then, of course, it produces H2CO3, which is called carbonic acid. Right? So the bicarbonate and the carbonic acid constitute a conjugate acid-base pair. This is the acid in the pair. This is the base in the pair. And the second pair is nitric acid with nitrate. This is the acid. And this is the base. Yes? All right. So, again, water is the fundamental example of an amphoteric substance. We've already seen these reactions acting with an acid. It picks up protons, produces hydronium. Reacting with bases, it can donate protons to produce hydroxide. So water participates in one or the other depending on what it reacts with. So what it turns out to happen, this is what I sort of alluded to earlier, because water has this property, it turns out that it can't help itself, and it reacts with itself in pure water to a very small extent. So in pure water, there's always a small percentage, very small it turns out, of water molecules that are transferring protons to each other. So you can consider then what we call the self-ionization of water, or auto-ionization, depending on what book you read. So two water molecules are bouncing off of each other, and if you actually write it like this, if you consider this picking up that proton, right, and releasing hydroxide, what happens is the water that picked up the proton becomes hydronium. The one that lost the proton became hydroxide. So technically it's two water molecules reacting with each other. They're in the liquid state, right? And then they produce hydronium and hydroxide. So what's going to be the relative ratio of hydronium and hydroxide? How much hydronium versus how much hydroxide? Anyone? So if you have this, is there going to be more of this than this, or more of this than this? They must be produced in equal amounts, right? Because for every one that gained, another one lost. So it's going to be as much of this as much of that form, right? As much of this. So these then will coexist. If we're talking about pure water, they will coexist at the same amount. So it turns out that at 25 Celsius, which is normal room temperature, the amount of hydronium is 1 times 10 to the negative 7 molar. 1 times 10 to the negative 7 molar. Very, very small number. Because the amount of hydroxide that is produced has to be the same, there's also 1 times 10 to the minus 7 hydroxide. Now, if we go back to this reaction, which is right here, you'll notice that water is in the liquid state. So we can define an equilibrium constant for this process, which is defined by the product of hydronium times hydroxide, molar concentrations. We do not include the water because it's a pure liquid. So we define Kw as the product of the concentrations of hydronium times hydroxide. In pure water, this is 1 times 10 to the minus 7. This is also 1 times 10 to the minus 7. Therefore, Kw at 25 Celsius is 1 times 10 to the negative 14. Again, at 25 Celsius, pure water, because these two have to be the same, this is the concentration of both of these ions. Now, this is an equilibrium like any other, it turns out. And Le Chatelier's principle applies. So if some acid from an external source, let's say you add HCl to the water, what happens to this equilibrium? Well, suddenly that substance, as displayed in the previous slide, is increasing the amount of hydronium, right? So this equilibrium is suddenly disrupted, and the amount of hydronium increases to whatever the acid that you added brings it to. But this is an equilibrium, so what's going to happen? Well, it's going to shift to the left. So therefore, what's going to happen to the hydroxide? The hydroxide has to drop. Okay? And how much will it drop? Well, it will drop to whatever value it needs to drop, such that the product of hydronium times hydroxide equals 1 times 10 to the negative 14. Because remember, the equilibrium constant must always be obeyed in terms of the relative concentrations of the substances. So an acid added from an external source will increase the hydronium. That forces the hydroxide to go down. To what point? To the point where the product of those two is going to equal this. Okay? The exact opposite happens if you add a base. If you add hydroxide, I add some sodium hydroxide to water. What's going to happen? Well, if I add sodium hydroxide to the water, the hydroxide in this equilibrium is going up from an external perturbation, right? I'm opening up a jar and I'm adding sodium hydroxide. Suddenly this goes up tremendously. Well, that forces this to go down. By how much? To whatever it needs to go down, such that whatever is here and whatever is left of that, when you calculate the concentrations, they're going to equal this value. So an acid solution will contain excess hydronium relative to hydroxide. And that's what makes it an acid solution. A basic solution will have excess hydroxide relative to hydronium. That's what makes it a basic solution. Okay? So because that product always has to be 1 times 10 to the minus 14, when you add acid and that hydronium has gone up, the hydroxide has to go down. When you add hydroxide, your basic solution has a hydroxide that's greater than 10 to the negative 7. That means your hydronium has gone down below 10 to the negative 7. The product of the two must always equal this value. Only in pure water is where they are the same, still equal the product 1 times 10 to the minus 14, but that's what we call a neutral. If it's pure water, it's not a solution, it's just a neutral liquid, let's put it that way. But you can have a solution of something that when you measure how much acid is in there, hydronium and hydroxide are the same. That solution is said to be neutral. Okay, neutral. So acid has more hydronium, more than 10 to the negative 7, hydroxide less than 10 to the minus 7. The exact opposite happens for a basic solution. If they're the same, you're dealing with a neutral system. This little cartoon illustrates this concept. So if you're in a neutral situation, they're both 10 to the minus 7. The moment you add acid, this goes down. The other one will go up. Notice how the scales are here with the 10 to the minus whatever. The product of the two will always be 10 to the minus 14. The exact opposite happens if you have a basic solution. Okay? So just to close, you can actually determine how much hydronium is present in a solution of a base by dividing Kw by the hydroxide concentration. You can determine how much hydroxide is present in an acid solution by dividing Kw by the hydronium concentration. Okay? So just to give you a heads up, next week you're going to be doing a lab on acids and bases. You're going to be learning about a concept called pH. pH, just because that's silly lights out that we had, we would have gotten to it. It's another way to measure hydroxide and hydronium concentration. We'll talk about that when we come back next week. All right. Yes. No, the quiz is up to chapter 6. That's it. End of chapter 6. Got the second?